Hi, everyone, and welcome to This Explainer. Today, we're unpacking a metric that is absolutely critical for any modern cement plant. We're talking about the thermal substitution rate, or TSR for short. Now, if you're anywhere near plant operations, you've definitely seen this acronym thrown around. But truly grasping how it functions on a mathematical level, well, that can completely change how you view your plant's efficiency and its environmental footprint. Here is our roadmap for today. First, we'll cover 1, the great TSR misconception. Then 2, defining thermal substitution rate. Third is our main focus. 3, how to calculate plant TSR. After that, we'll look at 4, benefits versus operational challenges. And finally, 5, finding the optimum balance. All right, let's jump right into section 1, the great TSR misconception, quantity versus heat energy. Okay, we need to clear the air right out of the gate here. There is this huge, really common misconception in the industry that if a plant simply feeds more RDF, that's refuse-derived fuel, or more biomass into the kiln, the TSR is just magically going to go up. But that's absolutely not true. TSR is not based on the sheer quantity or the tonnage of the fuel you're feeding. It's actually based strictly on the thermal energy. That means the actual heat contribution that those alternative fuels are giving to the kiln. To put it simply, 1 ton of coal does not equal 1 ton of RDF when we're talking about TSR. And why is that? Well, coal has a much higher net calorific value, or NCV, compared to RDF. So even if your feed rate is identical for both of those materials, the amount of heat they contribute is totally different. You literally can't just swap tonnage and expect the same thermal result. So now that we know what it isn't, let's move on to section 2, defining TSR. What is it exactly? Let's nail down the formal definition. The thermal substitution rate is the percentage of the kiln's total heat requirement that's supplied by alternative fuels and raw materials. We usually just call that AFR, instead of conventional fossil fuels like coal or pet coke. Basically, this metric is the ultimate indicator of our shift away from fossil fuels, showing us exactly how effectively a plant is actually using alternative energy. And the math behind this concept? It is wonderfully straightforward. The formula is just the heat energy from alternative fuels divided by the total heat energy input and then multiplied by 100 to get your percentage. This brilliantly simple formula proves exactly what we were talking about earlier. TSR depends entirely on those heat energy variables, not on how much heavy material is sitting on the wayfeeder. Which brings us to the core focus of today's explainer, Section 3, How to Calculate Plant TSR, a step-by-step guide. Let's walk through a real-world scenario so you can see exactly how this works in practice. Let's slow down for a second and really let this methodology breathe, because these 3 steps are kind of the ultimate recipe for tracking plant efficiency. Step 1, you calculate the heat input of each individual fuel by taking its feed rate and combining it with its net calorific value. Step 2, add all those heat contributions together to find your total thermal energy. And step 3, divide the heat supplied by the alternative fuels by that total heat input and multiply by 100. All right, let's plug some actual numbers into those steps. If we measure our inputs in gigacalories per hour, we've got our conventional fossil fuels, coal contributing 77.5, and pet coke giving us 24.3. And then we have our alternative fuels, RDF contributing 12.8, and waste tires coming in at 10.2. Following step 2 of our process, we just add all those fuel inputs together. So 77.5 plus 24.3 plus 12.8 plus 10.2, that gives us exactly 124.8 gigacalories per hour. That number right there is the absolute total heat input supplied to the kiln. Next up, we isolate just our alternative fuels. So we take the RDF and the waste tires. By adding 12.8 and 10.2, we get an AFR heat contribution of exactly 23 gigacalories per hour. And now for the moment of truth, step 3. We take our alternative fuel heat, which is 23, and divide it by our total heat, which is 124.8. Multiply that by 100, and boom, we have our calculated plant TSR, 18.43%. Thinking about that distribution for a second is honestly a bit of a reality check. I mean, despite actively using waste tires and RDF in the mix, over 81% of the kiln's thermal energy in the scenario is still relying heavily on conventional fossil fuels. It shows you exactly where the plant actually stands in its sustainability journey. Now that we've totally mastered the calculation, let's zoom back out for section 4, benefits versus operational challenges, weighing the impacts. Let's start with the benefits because they are incredibly compelling. By replacing coal and pet coke, cement plants score some massive economic and environmental wins. You dramatically reduce your dependence on fossil fuels, you lower CO2 emissions, and you help support sustainable cement production. Plus, it allows the industry to safely co-process industrial and municipal waste. This keeps stuff out of landfills, supports the circular economy, and here's the best part for the business side, it can totally optimize fuel costs. On paper, it's a complete win-win. However, there is a very real catch. You can't just crank up the alternative fuels and expect everything to run perfectly. Alternative fuels often have varying moisture content, totally different particle sizes, and fluctuating calorific values. If you let excessive AFR usage go unchecked, operators are going to face some gritty operational nightmares. We're talking unstable heat input, dangerous flame instability, highly variable burning zone temperatures, and just a massive increase in cyclone buildup and coating formation inside the kiln. The maintenance requirements can literally skyrocket. So, how do we mitigate those intense physical challenges? Well, the source material makes it crystal clear. Increasing your TSR has to be supported by 3 specific, rigorous operational controls. You absolutely must have good combustion control, highly reliable AFR feeding systems, and relentless continuous process monitoring. Without those 3 pillars holding things up, a high TSR will honestly just destabilize your whole kiln. Which brings us to our final section, Section 5, Finding the Optimum Balance, Strategic Operations. Let's shift the paradigm on how operators should actually be looking at their daily production reports. Ultimately, the thermal substitution rate is way more than just some percentage you log on a daily report. It's a barometer of your overall effectiveness. The objective on the plant floor isn't blindly maximizing alternative fuels at all costs. It's about finding this harmonious balance, keeping fuel costs low, maintaining strict kiln stability, preserving top-tier clinker quality, and improving environmental performance all at the same time. So I want to leave you with this provocative thought to chew on. As you look at your own plant strategy and you review those daily calculations, are you blindly chasing a maximum TSS or are you strategically targeting the optimum TSS? The difference between those 2 approaches is exactly what separates a struggling plant from a true world-class operation. Definitely keep that in mind the next time you're calculating your kiln's heat input. Thanks so much for joining me on this explainer. Keep learning, and I'll catch you on the next one.